All right, lesson 2.9. We're going to look at logarithmic expressions today. Specifically, we're going to look at what the inverse of exponentials are, which I'm just telling you right now, it's logarithmic. And we're going to talk about how to graph on a logarithmically scaled vertical axis. Now, a lot of you in Algebra 2 may have done this before. In Algebra 2, you may have done number 1, first learning goal. But I'm going to guess that none of you have seen number 2. It is a pretty neat little tool. We'll get to that at the very end. And I'll show you how that's useful. So first, the important concept that I want to grasp today is this. When you're doing algebra, again, there's a lot of notes here you can read on your own later. I'm just going to explain away through the math. When you're solving algebra, the thing you learn to do is the opposite operation. The true word would be the inverse operation. So here I have x plus 3 equals 7. If I wanted to solve for x without using some calculator tool like Photomath or Mathway or whatever, what would you have to do to solve this? You would subtract 3. You would find out that x equals 7 minus 3. Now we do that because the inverse operation to addition is subtraction. Okay, and then what about multiplication? If you had 3 times x, how would you solve 3 times x? Equals 7, I should say. You would divide. You would say that x is going to equal 7 divided by 3 because what's the inverse operation to multiplication? It's division. What about that we get a power here? We did cubing. It could have been anything. Could have been a square. Could have been whatever. Let's say you had x cubed equals 7. How do you get rid of a cube there? You would cube root it, and you would say x equals the third root of 7. Now, specifically for cubing, you would say the inverse operation is the third root. Or you could say cube root. I'll write cube root just because it says cubic over there. The cube root. Now, the new one today is for, here's a big word, exponentiation, which just means if something is raised to the power of x, your independent variable. How could I solve 3 to the power of x equals 7? What you would do is you would convert this to a log. What we're going to find out here is that x will equal log base 3 of 7. And so the inverse operation is a logarithm. So again, if you read these words, it'll say we've recently learned about exponentials and their properties. We're going to find these properties still work for logarithms after we've exchanged our x and y and solve from there. And I'm going to walk you through this math more here on the next slide. So how did I get log base 3 of 7? How did I get that? We're going to learn about that here. So if that was the important concept, here's the big idea. Just as we can write rational numbers in decimal form and fraction form, like meaning we can exchange 0.5 is the same thing as a half, we can also write equations that are exponential. We can also write equations in exponential form or logarithmic form. Exponential or logarithmic form. Meaning you can convert back and forth. They are equivalent statements. So here's the example. Any base raised to some power is equal to a number, and how we convert that is you'd say a log of the base to the number equals 8. Now what happens here, I want you to note, on the note, what it looks like is whatever the base is raised to gets exchanged. What the base is raised to gets switched, meaning the inverse switch. So notice here, what is the base being raised to? A. And C was all alone. Over here, what's the base raised to? C. You see how A and C got switched? That's what happens with a logarithm. Some weird little things you'll see is that if there's a base of 10, they're not actually going to write the base. So if just where it says log 3 and you don't see a little number there for the base, that means the base is 10. Okay. So if you do not see a base, what is the base? 10. If it says the word log, I should say. Because additionally, a natural log is if the base is e. So if you had log with the base of e, they will rewrite this as ln. ln stands for natural log. And oh my, I've realized I forgot the quotes there. Let's put that quote on there. It's called a natural logarithm. So ln means natural log. Okay, so with that, I'm going to walk you through quite a few different examples to make sure we can get this right over and over and over again. It's very simple mathematics. This is one of the easier operations to perform once you get down what you're supposed to do. So let's look here, example 1. It says convert the following equations from exponential form to logarithmic form and simplify, if possible. Okay, so starting here, which one, if I asked you, what's the base? What would you say the base is?
3.
3, that's right. So what's going to happen is the base is going to be raised to some power or exponent. Since it's exponential, I'll use the word exponent. And that's equal to some number right now. What we're going to do is switch it to log form. And log form, how it'll look is like this. You'll have log, and I wrote that in blue for intentionally because that's a new word that wasn't existing over here, with some little base. And the base will seem to be raised to the number, and that would equal the exponent. That's the relationship of what's about to happen here. These are inverse of one another. Let me put that in the middle here. Inverses. Meaning you're switching x and y. If the exponent is x here, and the number is y, well, over here, the number, what was y, becomes the new x, because you switch those two. The number is going to become your new x, and the exponent is going to become your new y. You think all by itself, because you're going to switch what was x and y. Okay, so back to the problem. It says 3 to the power of x equals 9. We need to keep the base, but we're going to switch the exponent and the number. So which one was my base again?
Wait.
3. But instead of 3 being raised to the x, what's it now going to be raised to? 9. And that would equal x. You can type that in the calculator, but my guess is many of you know 3 to what power is 9? 2. So this answer here is that x would equal 2. Now you can type that in the calculator to do that. Another technique that you're going to start seeing me do a lot is what I call upside down division. It's where when you have it, I do it from exponential form. I think it's easier because you're more familiar with it. You take the larger number and you divide into it with an upside down division by the smaller number. Which one's smaller, 3 or 9? 3. 3 can divide into 9 how many times? 3 goes into 9 3 times. So here's what that means in terms of exponential. These parts are like multiplying. This is saying 3 times 3 is equal to 9. Also stated 3 squared equals 9. Therefore, x is 2. Okay. So that's how you'll see me solve it by hand, is I'm going to start using upside down division. All right, what about this next one?
10 is the base.
10 is the base.
Why is your
So I'm going to first write the word log. We're going to convert it to a logarithm. So the base stays. Which one's the base? 10. What exchanges is the exponent and the number all alone, which in this case is the variable y. You switch those two, and so I have log 10. Now it's raised to the y, and that would equal. Can I simplify that one?
yes?
Actually, I cannot. Why can I not simplify? Because I have 2 variables, but only 1 equation. To simplify 2 variables, you'd have to have 2 equations. So that's just going to be your answer there. What about example C?
R is base.
R is the base. That's the important thing. So we're going to say we have a log with a base of R. Is it still going to be raised to the t? No. Now what's it raised to? W equals t. Now, truthfully, the way you would read this is you want to say log base R raised to W. How they would read this is they'd say log base R of W equals t. That's actually how you'd read that. Okay, what about this last one here? Which one's my base? Give everybody a chance to think about it. Which one's the base? Why is e the base?
Yes.
It's the one that has something raised. It has a lot of power. So you're correct. So you would say log of e. Does it still get raised to the 3x?
No. Y.
To the y equals.
Yes.
Now this I can simplify in two different ways. First, if you have log e, that's equivalent to log with the base of e is, there was a special logarithm. It was on the notes section of the previous slide at the very bottom. It's a natural log. So I want to say natural log. And if you write natural log, you don't show the base. You hide the base. Natural log y equals
Yes.
3x. Now there's one more thing I could do to simplify further. What's the 3 doing to x? How could I get that x isolated?
Minus.
I would divide. The opposite operation, the inverse operation would be division. And so we'll have x equals natural log y all divided by 3. Do it like this. X equals natural log y all divided by 3, like that. That would be your answer. Now I have 2 for you to try. Same concept of what we just did. I'll let you try to convert and simplify if possible. Now looking at example 2. Here we're going to convert from log form to exponential form and simplify if possible. So again, what we're learning here is how to solve without using InSolve or MathWay or something like that. So right now, could you type this into the calculator, press enter, and get an answer?
Yes.
Right now?
Numerical solve.
Without using InSolve or something like that?
No.
No. So what you would do is you convert it from logarithms to its inverse. To solve a logarithm, you'd go to exponential. So what's my base? 7. What's the power?
9.
9. 7 to the 9th equals x. Now, I don't know what that number is off the top of my head, but I'll let you type it in. That's going to be a very large number. 7, well, I almost gave away the previous answer, but 7 raised to the 9th power is going to be extremely large. That's 7 times 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 7. That's going to be really large.
It's 8 numbers.
8 numbers? All right, can you read them off?
4, 0, 3, 5, 3, 6, 0, 0, 7.
So I put a comma there. It's over 40 million. That's a really large number, isn't it? Okay, that would be the answer to that one. What about this logarithm? Could we solve this one? Well, how would we begin?
3 is your base.
3 is the base. What's it raised to?
X.
Now x, because we do an inverse operation, and that will equal
Y.
y. Now, is there anything to solve there? No, so you can leave it in this form. A lot of times if we have a y, we might write the y out front. So if you rewrote it this way, I would not complain. Y equals 3 to the power of x. Okay, what about here? Oh, this just says log and nothing else.
2 equals Y.
It has a base of 10. It's a hidden base. If it says the word log, but it doesn't show you base, the base is 10. So this is saying 10 raised to, sorry, when we convert out of the log, 10 squared equals y. Now I'm guessing y'all know what 10 times 10 is. Y would equal, oops, 100. There's that answer. And now finally, what about this one? It says ln. What does ln mean?
E.
E. Now, a lot of students, that means it's a log with the base of e. A lot of students, when they hear me say ln, think I'm saying Ellen, like Ellen DeGeneres. So if you start hearing, wait, what is he talking about? When I mean ln, I really mean, what's the 2 words? It's a natural log. In Latin, their order is opposite. This was Latin when they came up with it. So you know how a lot of things when you translate might switch the order around the words and stuff like that. They would said, I think it's logarithmic natural if you do a direct translation, but it was Latin people. That's why it's L followed by an N. But in English we'd say natural log. It's a natural log C equals 4. So we convert that, we would say e to the fourth power equals c. Now again, I don't know what that is, so type that into your calculator. And again, we're gonna get a crazy number here. Because e, if you remember, is like 2.71, give or take. So when you type that into the 2.71 times 2.71 times, I wouldn't type it in that way. I would do e to the fourth power. You hit that button on the left side of the calculator. Let's round it to the nearest thousand, meaning give me 3 decimals after you type that in, press enter.
34.598.
34 or 54?
54, sorry.
54.598.
Yes.
Okay, so what was the number after?
2.
2. So was it 8.2? Okay, good rounding then. Okay, with that, I'm going to take you to the second round of DOLs. I'll have you convert these two logarithms.
So
Yep, convert these two logarithms to exponential. All right, so I kind of dove into this, but I'm going to do it again. It says when a calculator is not available, oftentimes a logarithmic expression, a logarithmic expression is easier to calculate by utilizing its equivalent exponential form. So evaluate the following expressions without a calculator. Now, a lot of students would look at this and say, I don't know what to do here. So to solve it as an exponential, here's what I do. I don't have a variable right now. I'm just going to introduce the variable x. We're saying we don't know what that equals, and we want to know what does that equal. So one of the things you can do that makes it a lot easier to solve is convert it to exponential. If I was converting this to exponential, what's my base?
2.
2. What's my, is it going to be 2 raised to the 8?
No.
2
Six.
raised to the equals 8. And the reason we convert it this way is now it's easier to use upside down division to see what am I actually dividing into. So which is the larger number here? 8. And so 8 gets divided by the smaller number, which in this case happens to be the base. 2 goes into 8 how many times?
4.
4. And 2 can go into 4 2 times. So that means 8 is equivalent to 2 cubed. 2 cubed equals 8. 2 times 2 times 2 would give us 8. Now, if I do a little substitution here, I'm saying 2 to the x is equal to, instead of 8, I'm exchanging it with 2 cubed. Any guesses on what x is going to equal? X equals 3. Now, in our problem, did I originally have an x?
No.
No. So to be mathematically accurate, I would need to just say that this, let me just erase that. And we're going to say this now equals 3. Since the reason I'm saying mathematically equal is they never gave us an x, so I'm not going to include x in the answer. That right there is called the one-to-one property. If you want to write that down, 1-to-1 property. It states that once you get the base, 2 bases equal to one another, you can cancel out the bases and just set the powers equal to one another and solve from there. That's what I did there with the one-to-one property. All right, let's try the next one. Part B here. Slide. All right, B. So here, again, I'm going to introduce a variable for a moment. Since it doesn't have a variable, we're going to say 30 log base 5 of 3125 equals x. So to convert to exponential, I would say
5.
5 to the x equals 3,125. So you take the larger number, 3,125, and you divide by the smaller number, 5. Well, how many times can 5 go into 3?
None.
None. But 5 can go into 31.
6.
6 times, the remainder of 1. How many times can 5 go into 12? Twice, with the remainder of 2. And how many times can 5 go into 25? 5. So 5 times 625 equals 3,125. Do I stop there? No, I want to know how many powers of 5. So I divide this by 5 again. 5 can go into 625. 5 goes into 6
1.
with the remainder of 1. 5 goes into 12 twice, the remainder of 2. 5 goes into 25. So now we know 3,125 can be written as 5 times 125. Still going to keep going. 5, can it divide into 1?
No.
Can it go into 12?
2.
2 times, the remainder of 2. Can 5 go into 25? It's 5 times. 5 times 5 times 5 times 25. All right, let's break it down further. 5 cannot go into 2, but it can go into 25 5 times. That means 1, 2, 3, 4, 5. 5 to the 5th power is equivalent to 3,125. So 5 to the x equals 5 to the 5th. And because of the one-to-one property, we can now state with confidence that x equals 5. I'm just going to say 1-to-1 property real quick. And so for my answer, since x wasn't originally a part of the problem, I'm just going to erase my x there and say 10. My answer is 10. No, where did I get 10 from?
5.
Losing my mind. Answer's not 10. What's the answer?
5.
5. Goodness gracious. 5. Now, all these you could type in the calculator. The whole point here is, what if this is on a non-calculator part of the test? That's how you could do this. All right, what about log 4 of 32? Now, this one's interesting. Because, let's first convert it. 4 to the power of x equals
32.
32. So I first convert it like that. Now we're going to say the larger number is 32, not 34, 32, and 4 goes into 32 how many times?
0.
8. And 4 goes into 8 how many times?
2.
And we have a problem. What's our problem?
It's
4 cannot go into, it goes into, it doesn't go into an even number of times. So what you want to do is come up with a number that can go into all of these factors as well.
2.
2 can. So I want you to think of it this way. You can branch off of this if you want. Now I could redo it and just say, okay, let's do 2 into 32, which I'll do that in a second. But some students will just go like, this is how I was taught to do it. From here, 2 goes into 4 how many times? 2. 2 goes into this 4 how many times? And you don't have to simplify this 2. So that means 32 is 2 to the, how many 2's do you see?
5.
5. 2 to the 5th is equal to 32. And not only that, you could just take either 4, it doesn't matter. 4 is the same thing as 2 squared. 2 squared equals 4. Now I could do it over here, and you would see the same thing would apply. You'll get 2 to the 5th if I do it over here. 2 to the 5th. Okay, so how are we going to solve this? I'm going to convert this 4. What is 4 the same thing? 2 squared. And since it's power to a power, well, I'll get there in a second. Let's do that. 2 squared to the x equals 2 to the 5th. Let me extend my page here. No, that's not what I wanted to do. Sorry. I'm going to move this over just a tad. Okay. What was our exponential rule when you have a power raised to another power? So that means 2 to the 2x equals 2 to the 5th. And now we can use one-to-one property. And we could say 2x equals 5. That's one-to-one property. And finally, last step, how can I get 2 isolated, or the x isolated? I'm sorry. Divide by 2. So the answer is 5 halves. 5 halves. That becomes my answer right there.
2.5.
We're 2.5. Yep. Okay, last one. It just says log, but there is no base.
10.
If there's no base and it says the word log, it's a hidden base of 10. It's called the common logarithm. So to solve this, I'll put an xe here. So 10 to the power of x equals 1,000. Which one's a larger number? 1,000. So we take 1,000, we divide that by 10. 10 can go into this 10 one time. 0, 0. So 10 goes into 1,000 100 times. Can 10 go into 100?
Yeah.
How many times? Not twice. 10 times. There we go. And I can stop because they're all 10s. So that means, yeah. 10,000, 10 cubed is 1,000. Therefore, 10 to the power of x is equal to 10 cubed. According to the one-to-one property, x equals 3. And that's the answer to our logarithm. 3. So that is a way you can do this without calculators. How do you solve a logarithm? Y'all answer this question. I'm not asking rhetorically, I'm asking serious. How do you answer a calculator without, how do you answer a logarithm without the use of a calculator? Convert to exponential and then use upside down division. That's the easiest way to do so. All right. I said all right. Got more. Got to show you some more tricks. What about this one? Let's convert this. How would I convert this one?
4, 16.
The power of x equals 4. Not to be mistaken, I've said it a few times, but it's the first time you see it like this. You always take the bigger number and divide by the smaller number. So this time I'm taking 16, the base, and dividing by the number of 4. How many times can 4 go into 16?
4.
So 4 squared is equal to 16. That's what I'm substituting for 16. So it'll be 4 squared, power of x equals 4. What's our exponent rule when it's a power raised to another power? You multiply. So it's 4 to the 2x equals 4. If it just says 4, the power is 1. So I'm going to do one-to-one property. 2x equals 1 according to the 1-to-1 property. And now we have our answer. Well, not yet. How do I isolate this x? Divide by 2. So we get x is equal to 1/2. Okay, this one's interesting. Let's look at f here. I'm going to set this equal to x. So when we convert, what's it going to look like when we convert this?
3x equals 1.
3 to the power of x equals 1. And so you're supposed to take the bigger number and divide into it the smaller number. How many times can 1 go into 3?
3.
How many times can 1 go into 3?
3.
How many times can 1 go into 3?
3.
You see this infinite loop we're getting into? This doesn't work. Why does it not work? Because we're dividing by 1. So what do I do instead? If you think about this, there's another way of rewriting 1. You know what 1 is equal to? 3 divided by 3. Would y'all agree with that? Now, if it's 3 divided by 3, what's this power on this 3? That's 1, and that's a 3 to the first. So they're both 3 to the first, which is equal to exponential rule. What can you do if you are dividing by the same base? And so 1 equals, what's 1 minus 1? 3 to the 0. So 3 to the x equals 3 to the 0. I've exchanged my 1 with 3 to 0, which means after one-to-one property, x equals 0. So our answer this time is 0. All right, 2 more with some more tricks to see. Right. So 2 more to look at. All right, let's take a look at G here. All right, to solve this, I'm just going to say this is equal to x. All right, talk me through it. What would you do first? 4 to the power of x equals 1 over 64. Uh-oh, my battery. There he goes. Back. 4 over x equals 1 over 64. I'm going to do an exponential rule here. Do y'all remember what we can do with this? A negative exponent. Good. I'm going to say this is 4 to the x equals 64. Goodness, well, this is going really slow now. To the negative first power. It was 64 to the first. I'm going to raise it to the negative 1. And that makes it 64. Okay, so what's the larger number here? 64. So I take 64 and divide 4 into that. How many times can 4 go into 64? 4 goes into 6. 1, so the remainder of 2. 4 can go into 24. 6. There you go. So 4 goes into 64 16 times. Can 4 go into 16? How many times? That means 4 cubed is equal to 64. So I'll substitute that in. 4x equals 4 cubed. But that needs to be raised to the negative 1 power. What is our rule when you have a power raised to a power? You multiply. So we have 4 to the x equals 4 to the negative 3. We can do 1-to-1 property. X equals negative 3. And that's our answer here, negative 3. Last one. If we were to work our way through this one, we would say this equals x for now. When I convert, how would it look after I convert this one?
9x equals 2243 negative 4.
Okay, so I'll write out all the steps. So 9 to the power of x equals 1 over 243. How can I get rid of this fraction here? Reciprocal, or use an exponential rule here that you can take the reciprocal of your base. But I have to make my power negative. So now it's a negative power 1. Now I can solve this. I take the larger number. Which one's larger? 243. We'll do upside down division with 9. 9 can go into 243. Let's see. 9 goes into 24 how many times? Twice with the remainder of 6. And 9 can go into 63. Okay. How many times does 9 go into 27? 3. Uh-oh, we have a problem. I got 3, which is now smaller than 9. So what should I do? Break down 9 into factors of 3. 3 goes into 9 how many times? 3. Okay, so here's what this means. Just to make sure everybody's on track with me. 9 is equivalent to 3 squared. 3 squared is 9. That's what's showing right there. But 243, how many 3's do you count?
5.
5. So 3 to the 5th equals 243. So we're going to substitute both of these. So it's 3 to the power 3 squared to the power of x equals 3 to the 5th to the power negative 1. One of the last times I'll ask you this today. What do we do with a power raised to a power? So it's 3 to the 2x equals 3 to the negative 5th. How can I solve from there? 1-to-1 property. 2x equals negative 5. That's 1-to-1 property. Which leaves me with just one last step for this long slide. What's the last thing left? Divide by 2 to isolate. And so x that we added is actually going to be represented by negative 5 over 2. And there's your solution. Now, that was a lot there in that slide. That was a lot. Just got to see a lot of different tricks. With that, we're going to lead into your next section of DOLs. I'll let you evaluate these two. Okay, example 4. Now let's just go and make sure we know how to use the calculator. I did this all just on one page to evaluate the following expressions. Okay, so go to your calculator here, and here's mine. I'm going to go to new document. And when I open up calculator, I want to calculate log base 2 of 10. Log base 2 of 10. Now here's the question. Is that going to be an answer of 5? That would be saying 2 to the 5th power, which happens to be 32, not 10. How could we break down 10 if you try to do it upside down division? 2 goes into 10 how many times? 5 times. But that's not 2 factors of 2, so it doesn't work. You're gonna get a crazy decimal here. Okay, so are you getting the same number as me?
Yeah.
Now I want to make sure, we'll copy this over in a second. I want to make sure you understand why it's this crazy answer, not 5. Because if you wanted to solve this, you would say 2 to the x equals 10. And if you tried to break down 10, 2 goes into 10 how many times? 5. 2 goes into 5 how many times? 2.5. 2 goes into 2.5. Goes into this 2 once. 2.5. You see how we're not getting there? And you could keep trying, but you're just not, we just can't get there. So it's going to be 3 plus some extra. And so what's that extra? It's that right there. That's what it actually is. Okay, and what's the last one? It said log of 9. If it just says log, you can skip the base. What's the base going to be? 10. So 10 to what power gives me 9? There you go. I'm going to copy these and we will round them. It says round to the nearest 10,000th. So 10,000 as a number. How many zeros does 10,000 have?
4.
4. So you need to have 4 decimals when we round these answers here. Okay, so the first one, to round this to the 4 decimals, we need 1, 2, 3, 4. There he goes. Do I cut off the 2 or round up the 2?
Cut off.
Cut off. Truncated, I think, is the term for that. So it'd be 3.3219. Let me actually write it right here. 3.3219. That's my answer here. And on part B, this would be 0.95. Let's see here. We need 4 decimals. Do I round the 4 up or cut it off?
Cut it off.
Cut it off. So 42. That would be my answer here. Honestly, I should do a squiggly equal sign because we're approximating. I'll let you do now your next 2 DOLs. All right, so we've been dealing with learning goal number 1 all day, converting between logarithmic and exponential functions. We're going to finish up. Now I'm going to show you where logarithmically scaled vertical axis can be very much in handy. Okay, so here's a real world problem. This is data. I'm not going to read all this, but this is representing a population of European Americans from 1620 on up through, looks like 1820. So that's what the data is. It'll say it more in detail in the next problem. But let me just ask you this. If this is 1620, I'm going to go ahead and add this right here. This is 1620. What? This is 1620. And this is the year since 1620. How much of a difference is there between 1640? I know it's crazy because it says 20, but that's 1620 plus 20. What difference is there between this 20 and this 30? How much of a difference is there?
0 point something.
Can y'all tell? No, it's very hard to tell. On some exponential graphs, it's very hard to tell the difference. So what they do is they take the logarithm of this value. And so the population starts to look like this. So they'll represent in this with a logarithmically scaled axis. Now, can you tell a difference now before I asked you 20 and 30? Could you now tell a difference between 20 and 30? Yes, once they scale the population, you start to be able to get a difference. You can see differently. So if you're like thinking about what is 10 squared? 10 to the first. How many people would that be? 10. 10 squared would be 100. Notice how this is counting. What's 10 cubed? 1,000. So in 1620, there was less than 1,000 people there. But as you start going up, you can start seeing the difference. 10 to the fourth would be 10,000. Notice they're counting by the powers, not necessarily by an even scale as you're used to. So that's how it works. Okay, so now let's come to our actual problem here. It says example 5. I'm going to try to make my screen where we can see everything here. Where am I looking for? This one. It says the population data of English Americans in the United States since 1620 is shown above. So again, go to your data, put 1620 here so you're not confused. Put 1620 there. So for the number 20, what does that actually represent?
1640.
1640. This would be
1680.
60, 1680. This would right here would be 1700. Now, if 80 is 1700, where is 1800? 180 becomes 1800. And so this would be, if you add another 80 years, this is going to be right here, 1880. I did that just so you can have some scale. What this problem wants us to do is to plot these additional points on the table. So this population is shown here. We're given different values over here. So what I'm going to do is I'm going to convert this. What is my base here? 10. I want to know what is this number in terms of 10 to the power of x equals that. Does that make sense how I'm going to graph this? I'm going to say 10 to the power, I shouldn't say power of the x, I'm going to say power of y because it's the y-axis. 10 to the power of y equals this. So how do I convert this? How do I get y isolated? Log. We're going to say the y value will equal the log. Do I have to write a 10 if it's base 10?
Yes.
No, you can skip that. Log of 17,069,453. That's where we're going to get our y value. This x value, let's actually convert this to an x value. 1840 is going to be the same thing as, if this is 1820, this will be 240. The x value is actually going to be 220. Okay, so let's go to our calculator. Oops. And find out where this value should be. So log of 17,069,453. No, goodness. You could skip a 10 or you could put a 10 there. 17,069,453. Hit enter. Are you getting 7.23?
Yes.
Now that's the power I'm looking at. That was the y. 7.23. I'm going to put right here. Y is approximately 7.23, and that represents the power. So if I went over here, I would be looking just above 7. Let's just say that's 23, and I would need to line that up with 1840. That point where they intersect, that would be that first point right there. That's where that would go. Okay, now let's find this next one. I want you all to type that in, see what you come up with. Y equals log 31,443. I didn't do 23, sorry. 3321. What is y approximately there? 7 point what? 497. So let's just say 7.5. So now I'm going to go to 7.5. So I want to say maybe that's about 7.5, maybe you're in there. And I need to go to 1860, which means 20 years over. This next intersection is our second point in red. And finally, our last logarithm here.
0.7.
Okay, let me write out the number. I forgot to write log. Log 50, 189, 209. What do you get? 7.7. Okay, so I need to go up just a little bit higher. Let's say that's 7.7 there, and I go forward to 1880. So the intersection of those 2 points, that would be where that point goes right there. Now with all that, that's how you graph these. I'll let you do your DOL. Notice on yours, I gave you a few more lines to help you out. Between 1 and 10, they count by ones. So it goes, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This would be 20, 30, 40, 50, 60, 70, 80, 90, 100. And this would be 200, 300, 400, 500. Notice I put that on there. I want you to plot those points for me, please. I'll add one more thing over here. All right, your last DOL. Plot those points.